Hi, and welcome to Unit 5.4. This is part 2 of 4. In part 1, what we looked at were buffer solutions, what they are and how to make them and why they're important. In this, we're going to learn about the language that we use to sort of quantify acidity and basicity, because this language is going to be important throughout the unit. So I want you to first start off by filling out the know and want to know column of this KWL. What do you want to know about these terms here that we use to quantify acids and bases? So pH, POH, Ka, Kb, pKa, and pKb. Pause the video now, and when you press play, we'll go right into the lesson. All right, so now that you finished filling out your know and want to know, let's dive in. Let's start off by learning about pH and POH, things that you may already know. So here we have sort of two scales. On the bottom, we have the pH scale going from 0 to 14. And at the top, we have the POH scale, which could also be written with the 0 here and then going to 14 here. But it's flipped for a reason. So the 14 is on this side and the 0 is on that side. What you may know about pH is that the lower the pH, the more acidic you are. And that means the higher the pH, the more basic you are. And the same thing can be true about the POH. The lower the POH, the more basic, the higher the POH, the more acidic. So what are pH and POH? pH is the negative log of concentration of H+, and POH is the negative log concentration of OH-. They sort of measure the concentrations of H+ and OH- in solution. Now, one thing that you may be curious about is, well, why did we flip the scale in this image? Why did they flip the scale? Why was the 14 over here and the 0 over here? And that's because of a very important relationship between pH and POH. Let's say you have an acid that has a pH of 4. Its POH is going to be 10. Or let's say you have a base that has a pH of 12. Its POH is going to be 2. So do you notice the relationship here? Essentially, the sum of the pH and POH are always going to equal 14. So a pH of 4 and a POH of 10, you add that together, it gives you 14. A pH of 12 and a POH of 2, you add that together, it's going to give you 14. So that's why they wrote the scale that way, sort of show that relationship. And that relationship is important, along with knowing these equations. POH equals negative log concentration of OH-, and pH equals negative log concentration of H+. Like, these three equations are important that you need to know for pH. And the cool thing about the 14 equals pH plus POH equation is that you can use that to go, like, if you have the pH, you need to find the POH, or POH to find the pH. So all three equations, this one here, and then these ones as well, are important. And you are going to use all three of those equations to answer this for example problem. So first I'm going to have you try it on your own. So just take a moment, pause the video, read through it, see if you can do it. And then when you come back, we'll talk about how it's done. Okay, so we're given the pH of an acetic acid solution. We're told it's 4.9, and we want to determine the concentration of H+. So to determine the concentration of H+, concentration of H+ equals 10 to the negative pH. Now you may be wondering, well, where'd you get that from? Powers of 10 are the inverse operation of logs with a base 10, which is what the log we're dealing with here. When there's no base written down for a log, you know it's base 10. So essentially this is the inverse operation needed to solve, and I'll just go back real quick, this equation. Okay, it's the inverse operation needed to solve this equation. Then you were given this value, the pH, and you needed to solve for the concentration of H+. Okay, so that's how we got that. All right, so now we have 10 to the negative 4.9, which is our pH, and that's going to give us a concentration of H+. For POH, we use the relationship 14 plus equals pH plus POH, and when I solve that for POH, I get POH equals 14 minus pH, and then it easily gives me a POH of 9. And then finally, concentration of OH-, we do it sort of the same way we did for the concentration of H+. 10 to the negative POH gives you the concentration of OH-. Okay, so here to quickly summarize things that we ought to know, and this slide has pretty much summarized it. So you can take a moment, to sort of read through this summary. And then you could pause the video as you need, and then we'll come back, we'll go into the next topic. Okay, so next we're going to move into Ka and Kb. Those are some other quantifiers, and I also included Kw, which is the equilibrium constant for the ionization of water. In fact, all of these are equilibrium constants. So at this point, whenever you see a capital K, and the capital K is equal to something, there's no number in front of the capital K, like 300K, that would be 300 Kelvin. All other capital Ks here are equilibrium constants. So Ka just means the equilibrium constant for the ionization of an acid. Kb, it's for the ionization of a base. And Kw is the auto-ionization of water. So let's see what we mean by that. When we say ionization, what we're talking about is when you dissolve that acid or that base in water, what happens? What ions is it going to break apart into? And so our first example here, we have sulfurous acid, H2SO3. I want you to try this out, see if you can do this, and then we'll come back together. So when H2SO3 is dissolved in water, what does it ionize into? And then what's the equilibrium expression for it? Okay, so when H2SO3 ionizes, it forms HSO3 minus and H plus. Now, if you wrote the product as SO3 2 minus plus 2H plus, that's not correct, because remember, weak acids, they break down one proton at a time. So if you wanted to form SO3 2 minus, you would then need to write another equilibrium equation where HSO3 minus is on the reactant side, and that breaks down into SO3 2 minus and H plus. So with that being said, so this is the correct ionization equation. And then when we do the equilibrium constants, it's products over reactants. And so this is what it looks like. All right, let's try it for the equilibrium constant for base Kb. If you have a base like NH3, remember for amine bases, we need to show where the hydroxide is coming from. And we do that by adding water into the equation, liquid water into the equation. So that's why that's here. With that being said, what happens when you dissolve NH3 in water? What are the products? You're going to pause, and you're also going to try for the Kb. Great, you should have NH4 plus and OH minus as your product. And that makes sense because remember, bases make OH minuses. And then this should be the Kv. We don't include the H2O because it's a liquid. We only include aqueous and gases in our equilibrium expressions. Okay, let's move on now for water. And this one I'll sort of do for you, at least for the first part. You can come up with the Kw. So water, it turns out, most of water in water is H2O, but some of it will sort of react with each other, where one will act as an acid and give away a proton, other one will act as a base and accept a proton. And so this is what the products look like. So this is the product of a water that accepted a proton. We call this hydronium. And this is the product of when water donates a proton, we call it hydroxide, right? And you've seen hydroxide before, but maybe hydronium not so much. Hydronium essentially is whenever we say H plus in solution, like that's what the H plus really is this H3O plus if it's in solution. So we oftentimes will just abbreviate this as H plus. With that being said, now that you know the ionization equation, I want you to try for the Kw. Great, you should have H3O plus, concentration H3O plus times concentration of OH minus. And we don't include water because it's a liquid, so there's no reactant side. So if you wanted, you could put this over 1, or you could not. And if you're not putting it over 1, you can actually just remove that fraction line. Okay, so now let's go into how we relate Ka and Kb KB, we can use the equation that the Ka times Kb is equal to Kw. And Kw is a constant. At 25 degrees, it's 1.0 times 10 to the minus 14. And you can always make that assumption it's going to be this value unless you're told otherwise. So this is a constant value. So that's basically saying 1.0 times 10 to the negative 14 is equal to Ka times Kb. And just like with the 14 equals pH and pOH equation, you can sort of use this equation to calculate one from another. So let's try this for example. You're given the Kb of NH3 is 1.8 times 10 to the minus 5. You want to know what is its conjugate acid and determine the Ka of that conjugate acid. So you're going to pause the video now and you're going to try this out. And when you press play again, the answer will be revealed. Okay, so starting with the conjugate acid NH3 is NH4 plus. And to determine the Ka, you take the Kw and divide it by the Kb. And that will give you 5.6 times 10 to the negative 10. Okay, so a couple of final notes here before I have you try the next CFU. It's important to note that Ka and Kb are inversely proportional, meaning that as one increases, the other one decreases by the same factor. And pOH and pOH, they're not inversely proportional, but as one increases, the other one decreases. And so again, we can use these two equations. Now, it's no coincidence that the equations all have this 14 in it, and that just has to do with the fact that we're dealing with a water solution. So these values would be the same. All right, now I want you to try this CFU. This is a super important skill, and that skill is qualifying the values for these quantifiers based on the strength of the acid and base. So knowing, if I have a stronger acid, what's going to happen to pH? What's going to happen to pOH? What's going to happen to Ka? What's going to happen to Kb? And the same thing for base, like what's going to happen to them. So this is like a qualitative thing. So you're going to pause this video now. When you press play again, the answer will be revealed. Great. So I added 2 more columns just because this sort of explains some of the things. As acid strength increases, you have a greater concentration of H+, which means you're going to have a lower concentration of pH. As concentration of OH-, as acid strength increases, OH- decreases, so the pOH is going to be higher. All right, because these sort of work opposite to each other. Then for the stronger the acid, the more the acid ionizes, so the greater the Ka. That means like the reaction shifts more to the right. And then the smaller the Kb, since these two are inversely proportional. And the opposite is true for the base, so you can take a look and see what's written here. But again, this sort of skill is important because you're just sort of expected to be able to qualify these things based on your knowledge. All right, final note here, going into pKa and pKb. This is something that I don't think we have talked about before, but the pKa is the negative log of Ka and pKb is the negative log of Kb. And essentially, they sort of like in the same way that pH and pOH measures concentration of H+ and concentration of OH-, they sort of do this for the Ka and Kb and figure out like which ones will be more acidic, have a higher Ka, and which one will be less. And they will, just like pH and pOH, the lower the pKa, the higher the Ka, the stronger the acid, right? So the ones with the P sort of work opposite to what you would think they would do. The other thing to know is that pKa plus pKb is equal to 14. And that is, again, a handy-dandy equation. Okay, so you may be wondering why do we use these P's? They're kind of confusing. Like if it's more acidic, pH is lower, or if you have a higher Ka, pKa is lower. Like why? Okay, so let me tell you why. Essentially, what it does is it sort of helps us wrap our head around the numbers. If you measure acidity or basicity by the concentrations of H+ or OH- respectively, you're going to have a wide range in concentrations because you have a linear scale. So it can go from, let's say, for example, 1 times 10 to the minus 10 to 1 times 10 to the positive 10. But if you use the logs, then what happens is it's a much smaller scale, and that's why we use logs here. So it's going to go from 10 to the minus 10. And that's easier to see. Oh, I'm going from 10 to the minus 10. Like I can really wrap my head around those numbers. as opposed to the big numbers. And the same thing for the pKa and pKb. Again, Ka for strong acids can be really large, and or for weak acids can be really small. So again, just makes these numbers easier for us to see. Why did they use a negative log? I'm actually not sure about that. That's a good question. Maybe something that you could research and explore, but it is what it is.